Hi, I'm Sanghyun from Soongsil University. Today I'm gonna talk about our work in progress study title with Overcoming Capacitance Constraint in SSD. This is a joint work Soongsil University, DGIST, and Syracuse University. Historically, storage devices have been equipped with a small-sized volatile buffer to cache translation information and buffer write request. However, a volatile buffer loses their data upon a power failure. Enterprise-class SSDs protect the volatile buffer using capacitors. When a power loss is detected, it flushes the buffer data into the specific area in the flash using capacitors. This technique is called PLP. However, the reliance on capacitors is not sustainable as the increase in SSD capacity far outpaces the increase in capacitor density. The graph on the left shows that the SSD capacity grew 50 times in the past 5 years. In contrast, the density of capacitors only grew by 10 times in the past 45 years, a near 50 times lower growth rate. As a result, it is necessary to rethink how SSDs are designed with respect to the flow scaling of capacitors. With this motivation, we present a novel SSD design that works efficiently under capacitance constraints, like David, who defeated Goliath with 5 pebbles. This slide overviews the David SSD architecture in comparison with current PLP-enabled SSD. The current SSD typically protect the entire DRAM using capacitors. David SSD also fully protect the user data because it is not recoverable when it lost, but it protects the mapping table partially, by so doing reducing the capacitance significantly. When the dirty memory footprint of the mapping table goes beyond the protected range, DAI forces them to NAND flash, thereby ensuring their persistency even with a limited number of capacitors. In this architecture, it is needed to minimize the flush cost of the mapping table caused by the capacitance constraint. To realize this goal, we exploit the deep queues available in today's storage protocols. While older interfaces such as SATA and SAS only supports up to 32 and 245 command queuing, respectively. NVMe allows up to 64K command per queue. Such ample queuing allows us to implement efficient buffer management that minimizes the amount of data that need to be protected by the capacitor. David SSD reschedules user write such that mapping entry eviction becomes more efficient by aggregating data update. This example shows how David SSD manages write requests within a buffer. If the user write are processed first in, first out, mapping table can be randomly updated during a time window, resulting in a large 30-page footprint. In David SSD, we batch the write request whose mapping table page is same. This makes mapping entry eviction more efficient by aggregating data update. As a result, people incurs 5 times flushes, while David only has 2 flushes. Likewise, David SSD substantially reduces the amount of the mapping table related write traffic, and in turn improves the overall performance. To implement the David SSD architecture, we define the costs of each buffer data like this. The cost is set to 0 if its mapping table page is already dirty. Otherwise, the number of requests associated with a mapping table page. We prioritize a request with a similar cost because it minimally increases the dirty memory footprint of the mapping table. This feature is implemented by 2 data structures, a linked list that maintains requests with a 0 cost, and maxip, which helps to locate the request with the smallest non-zero cost. As a proof of concept, we implemented David SSD by extending FMU, which is an SSD emulator using DRAM. The capacity and user buffer is set to 64 GB and 4 MB respectively. In our study, we protect only 1% of the mapping table entries. We measure the IOPS using FIU benchmark by writing 90 GB data into the 30 GB range. We can confirm that the overall performance improved. The result confirmed that David works efficiently in situation of high locality and large footprint like JSD workload. Since sequential workload is already scheduled, we confirm that the DAO's performance is similar to that of people. As a future work, we plan to elaborate our work in more details, performing sensitivity analysis for various parameters, or rethinking mapping table eviction policy for our architecture. Thanks for listening.